Last time we looked at the sum of two random variables and its distribution. That reduced down to the convolution of their densities. If you have two densities, you simply convolve them if they are independent. If they're not independent, you just have to do a double integral. If you have an identical or just independent random variables, you would do a convolution and convolution of the integral. Now we move on to the show distance. The ratio of two random variables. Suppose x and y are two random variables. X has a PDF, fx of x, and y has a PDF, fy of y. I am going to assume that x and y are independent. And we want to find the distribution of the ratio of the two random variables. So, first approach would be the CDF approach. Let's say the random variable r is less than or equal to r. And the probability of x over y would be less than or equal to r y. Sorry, x over y would be less than or equal to r, which would imply x is less than or equal to r y. And we would end up having fx or uppercase y, not lowercase y. So that would imply that that probability would depend on uppercase y. If it was just lowercase y, we could do the transformation that we did last time, right? Univariate transformation. Remember the square root transformation? Easy. But that's not the case here. We actually have a random variable. You can't simply take this value and plug it in this CDF of x and get to the answer. We have to integrate it one more time using a conditional distribution and whatnot. So what is the easier approach? The sum of two random variables. We did that using a bivariate transformation. I'm not saying that that is not possible, doable, but this is much more effective. Really doesn't matter. So I'm going to define u to be x and v to be y divided by x. If I rewrote this, v times x would be equal to y. X is nothing but u, so vu would be equal to y. Y would equal u times v. The random variable y has now become radioactive. I'm glad one person got it. What did we do after this? Well done. The sum of two random variables. We started by calling one as u, the other as v. And after we did that, what was our next step? MGN. I did the joint distribution of u and v. So the joint distribution of uv evaluated at lowercase u, lowercase v is simply, or can be written, in terms of the joint distribution of x and y, x evaluated at u, and y evaluated at u times v. Are we done yet? No. What are we missing? The Jacobian, specifically the determinant. We have to put the absolute value. Density cannot be negative. So take the derivative of x with respect to u, I'll get 1. With respect to v, I'll get 0. Derivative of y with respect to u, I get v. With respect to v, I get u. Yes. I don't know how to write a proper lowercase v.
They're the same, it's larger or smaller.
Exactly, right.
Just put a little y on the left side.
What do you do?
I put like a little y.
Oh, like this? Oh,
Yeah,
that looks like n.
It's not.
I mean, I could do that, but that's like new. So determinant is u. And that would be the last step here. But are we trying to find the distribution of, or the joint distribution of u and v? No. What are we trying to find? We are going to, we need to find the distribution for v, because that has the ratio of the two random variables. How do we find the distribution of v if you have the joint distribution of u and v? Integrate. pretty standard. We've been doing this for a while. This is how I did joint distributions. We have to integrate with respect to both u and v. What is the integral? Oh, excuse me, should we integrate it with respect to u or with respect to v? U? Why do?
We're trying to sum out the u.
We're trying to get rid of the u and have the v. So in general, I can write it that way. In terms of x and y, this would simply be u, uv, du, and you have u. At the end, there is an integral involved, there is a joint distribution involved. Same logic would come into play here. You need integration, joint distribution, but it's just extra work. So the CDF approach is effective if you do univariate transformations, such as location scale, square root, logarithmic, power transformation. But if you have more than one variable, we have to stick to this approach. Since x and y are IID, and that particular condition is very important in any stats course, doesn't matter this one, upper level, graduate level. If IID is not specified by default, we're going to think that x and y are some two distributions, excuse me, two random variables. I can't simply make an assumption. Either by the nature of the experiment or the study, I determine that they are IID, or I conclude that no, that those two variables cannot be independent. Good example in practice, let's say lung cancer, and you have smoking, drinking, and what else? Throwing age, right? So you collect a bunch of data or whatever. I can't simply say the risk of lung cancer is independent of, smoking. We know that there is some sort of dependence between the two. In that case, we will need a joint distribution. And that is the integral that we would use to find the ratio of two random variables. But the key here oftentimes comes down to recognizing the limits of integration. So if we mess up the limits of integration, then we're going to have some issues. Good.